transfer and frequency response functions can be very useful to determine the system's response to random inputs, right? So up to this point, we have solved for things that are deterministic. Right? So deterministic means for a known time t, the value of our input f of t is precisely known, right? So we have a understanding, or we don't have an understanding. We absolutely know that for a given time t, we know what our input force is, right? But now we want to look at random responses, right? So for a known time t, the value of our input f of t is only known statistically, right? So we don't know what our input is. So for a random response, f of t is known statistically, or is only known statistically. Right? So to expand a random signal to signal with no obvious pattern, right? That would make sense. If I tell you something's random, there's no obvious pattern. For these types, it is not possible to focus on the details of the input system. So as we do with a deterministic signal, so rather the system is classified and manipulated in terms of our statistical properties, right? So we're going to solve this in terms of statistical properties. All right, so randomness and vibration analysis, or really anything in life, can be thought of the result of a series of results obtained from testing a system repeatedly under various inputs under varying conditions, right? So in these cases, one record is not enough, and you have to have multiple tests to describe a system. For instance, I had an interview once with a guy who was from Virginia, but he had just moved to, where was he? Where were we? New Jersey. At Stevens? I almost went to work in New Jersey. Aren't you guys so happy I'm here? Actually, I'm happy I'm here. Property taxes in New Jersey suck. I can say that. I live in the South. So, yeah, anyways. But he spent a lot of his career, I think I've talked about him before, he spent a lot of his career doing F-16 loadouts, right? So you put equipment on an F-16, and then you shake it on a shake table, and you see what happens. But they don't do one sinusoidal sweep, and they don't do one white noise, right? They do lots and lots and lots and lots of vibrations for days and days and days on end, and then they gather up all the data. And when he started his career, I believe he went to, I think he did his PhD at Johns Hopkins. You know, his job was to compile the stacks of cards, the Fortran cards, run them through the computer, right? That was his first job as a master's student. So, you know, now there's a website called Stack Exchange. Do you guys use Stack Exchange? No? Okay, well, it comes from back when, you know, you would trade code and you would just give someone your stack. You have your stack of index cards. So that's what he originally did, was vibration analysis on, I don't know what. I don't think, it wasn't the F-16 at that time, definitely. But these are people, you know, people have done their whole life on this. So I actually have a student who was in this class 2019, and now he works at Raytheon in New York. And that's what he does. He does vibration analysis of stuff. I don't know. He doesn't tell me. The one time I talked to him, he didn't tell me what. But he does vibration analysis, right? So his first job for the first 2 years of his first year of his job was doing vibrations analysis. So he actually found the notes, and he was asking me questions, and I said, well, if you're doing this professionally, I would recommend Gao's book. He has 600 pages on vibrations. I have 150. So that's who you're going to want to reference. But so these are things that we do, right? So we can go ahead and look at a plot, you know. So we've been doing deterministic signals. Right? And now what we want to move to is something that is much more random. And I'm going to draw this as a line, right? But it really shouldn't be. It should be points, right? They're not connected. But that's our signal, right? It's moving kind of through time, and there's no real way to know at any given point where we are. So, however, we can describe this statistically, right? So what's the first statistic that you look at this and say, oh, I know something about this signal? What's your first thing? Right? If you're asked to describe this signal, how do you describe it? So if you're asked to describe it mathematically, I want numbers. The amplitude, I mean, but there's lots of amplitudes, right? So max is a good one, but you know, how often does your max happen? Once. Yeah, so like the average, right? The mean. Like we know, well, we can figure out what the mean of the signal is. And that's a good statistical number to describe a signal, right? So we're going to call that the mean of a random signal x is, so our mean is our expected value of x. You guys have an undergrad statistics class? Have you taken it already? Okay. So mean of the expected value x is equal to x bar, which is equal to the limit as t goes to infinity of 1 over t, capital T, the integral from 0 to t of little x of t dt. So where t is the length of the time of the data collected. Right? So that should make sense. If I collect my sample, let's get a good one. So if I collect for this t, right? This is my average. Mathematically, that's correct. But I need to collect for a longer t to get a better average, right? So if I collect for this t, kind of starting at the same point, but let's come out to here. Maybe this is my average. That makes sense? So the length of time that you collect for is very important. So you don't get your average until you take until your t goes to infinity, right? So you'll never, quote unquote, have your average, but we can get pretty close. Therefore, the signal not centered around 0, we can obtain a 0-centered signal, right? Or we want to obtain a 0-centered signal, right? So often we're just going to subtract the mean out of our signal. That's super easy to do. We're just going to call that x prime of t, back in our time domain, is equal to x of t minus, let's just go with the x bar notation then. Right. E is expected x bar, right? So this gives us a signal centered around 0. So we're no longer, off-centered if we need to be. So as we mentioned before, the input is, it's important to consider whether the input is stationary. And this is the debate we have every Monday, right? What is a stationary signal? A signal is stationary if its statistical properties, usually expressed as its mean, do not change with time, right? So a stationary signal may look completely random, but if our properties are constant through time or relatively constant through time, then it's a stationary signal, right? A signal may look completely random, but if its mean is changing or its standard deviation is changing, then it's going to be a non-stationary signal. But of course, some of that kind of depends on how long you consider your period for, right? How long do you consider your t? So the relatively short t, there's some argument that could be made that this is a non-stationary signal. But if your t is long enough, this is going to be a stationary signal. Yeah.
I understand why you want your feet long to like get like a overview pretty much. You get like a smart sample, but does that not kind of decay your data? What if you're like vibrating in a dangerous range for like a short period of time, but you're taking like days worth of data, and for like, I don't know, 30 minutes you were vibrating at like this dangerous amplitude, but it's lost in the data because you have this outlandish period of time you're recording.
Yeah.
So not entirely random.
It's not entirely random. That's a really good example. And that's one of those hard, questions, right? So that's where, an engineering judgment comes in. And we do lots of things to kind of process that data, all right? So like if you're running something like that, you might look at your data with like a spectrogram. SPECTR, spectrogram, or you want to say thank you. That's a new homework problem, and it's a good one. I have a YouTube video of a vibrating beam, and then I'll give you some Python code or MATLAB code, and we'll do a spectrogram, like at the end of class. It's not a big deal. Or like a wavelet analysis is another good one. And these are ways that we kind of look at the signal or do more signal processing, right, if it's of interest. If you are interested in signal processing, I teach machine learning over the summer. Don't know why. I don't need the money. I don't know why I signed up for more work. But if you want to take machine learning over the summer as a 500 level class, you can. Counts for a tech elective. Make sure you take it as a 500 level class, because that way if you stay for grad school, it's one less grad class you have to take. And if you don't stay, it doesn't cost you anything. You just have to have like a GPA of like a 3.5, 3.2, something like that. There's some GPA cutoff, but anyways, in all of your classes, you should be taking when you take your elective, you take 500 level classes. You take like, this being recorded, take like CAD and CAM. Those are boring. Don't take those. Take classes that are challenging, that are, you'll learn something mathematically, right? If you don't know how to use SolidWorks or Fusion by now, you're screwed anyways. So having CAM, if you really want to do manufacturing, like my hobby is machining, and I actually have a 1-year tech degree to be a machinist, right? So I guess I had a CAM class. But anyways, take challenging classes. Also, there's a lot less people in them. But if you want to take machine learning, you can take that. Then what else is offered? I teach controls in the fall, 500 level controls if you want to take controls with me. Lucy teaches smart structures. She's really good. That would be an interesting one to take. And so you might not know, but like at the University of South Carolina, this is probably one of the best places in the world for smart structures, with Dr. G, and then Lucy was his student. So we did a proposal the other day, which didn't get funded. But one of the comments for the reviewers was, I note that Dr. G is on this, and he is the world leader in smart structures. So even though we weren't selected for funding, I was kind of like, oh, that's kind of cool. So if you want to take smart structures, this is a good university to take it at. It's also a good university to take CAD and CAM. I'm not going to fault you or track you down. But yeah, so that's a good question, right? Like, what do you do? How do you set that? That's a signal processing thing. That's an engineering thing. And that's something that we should explore some more. But for right now, it's just kind of an open question. I'll leave it at that. So another important variable is the variance, right? Or mean square value of a random variable. And so your variance is expressed as E to your signal minus your mean x bar squared, right? So we can put this in terms of t, which is the limit as t goes to infinity of 1 over t, 0 to t, x of t minus x bar squared, take our derivative with respect to t. and provides a measure of the fluctuations of the signal x of t, right? So if the signal is expected to have a 0 value, then so if the signal is 0 and the expected value is 0, then we have a variance of 0. So that makes sense, right? If the signal has an expected value of 0, or so let's say if the expected value of x is equal to 0, then x squared is equal to x bar squared, which is equal to limit as t goes to infinity of 1 over t integral from 0 to t x squared t of dt. Right, so this leads to the calculate of the RMS of the signal. So the root mean squared of the signal. So the RMS of the signal is x. RMS is equal to the square root of x bar squared. Mean squared root. When you guys say RMS, you know, the most common thing that you think about with RMS is like the outlet in the wall. So what's the voltage at the wall? 120. Yeah, what's the maximum voltage at the wall though? What is that 120? It's a sinusoid. Well, so the mean's going to be 0. No. Your maximum voltage at the wall is about 170. Yeah, it's the RMS. So that 120 is your root mean squared of your signal, right? So, you know, because it's going in and out, in and out, in and out. So its mean is 0, its max is 170, but for some reason we take the RMS as the value. So 120 RMS is what's at the wall. Yeah. This T is period. Well, no, this T is the length that you take your data over. I see what you mean. It's not like the period of the signal, because we're really kind of interested in random signals here, and they don't particularly have a period. That makes sense? Okay. So that gets us to RMS. Now, considering a non-stationary signal, right? So what's the stationary signal? What? No. So a stationary signal is a signal where your statistical properties of the signal remain unchanged, right? So it would be random noise, but your mean's the same, your variance is the same, your RMS is the same, right? A non-stationary signal is where your statistical properties change through time, right? So let's consider a non-stationary signal. An important measure of interest is how fast that variable changes, right? Does your mean change 100% in a second, or does it change 1% in a second? Those are very different mean changes. So this is important to understand as it provides context for how long a signal must be sampled, right, before you can get a meaningful representation of the signal to be calculated. So we want to for a non-stationary signal, an important measure of interest is how fast does it change? right? And so there's lots of ways we can quantify this. But one way to quantify how fast it changes is, we will use the autocorrelation function. Use autocorrelation. No, a time invariant system is a system that does not change through time.
Yeah, within that, we the same thing, but in like the context of a signal.
At the stationary signal? Maybe. I mean, but no, because a stationary signal could change. Well, it depends depends what metric to use for stationarity, right? If you only take your mean, your variance could change. I think they're kind of best left separated, those two concepts. Yeah, that's a good question, but yeah, we'll keep them separated. So an autocorrelation function, we write this as, this is where the math in this class starts to get a little hand wavy, RXX, so that's the autocorrelation function of your variable x, right? So if our variable is y, it would be RYY or RZZ, but we're dealing with x. As a function of tau, that's the Greek letter tau, is equal to the limit as t, which is not our period, but the length of our sample, goes to infinity, multiplied by 1 over t, it just tells you that we're averaged about t, for the integral from 0 to t, as one would expect, of x of t, right? We're concerned about x, multiplied by x of t plus an offset, which is tau, right? And then all of this is going to be with respect to dt, right? So we want the integral with respect to time. And so what we have is a comparison where we have the product between our signal and our signal at a specific offset in time, right? And then we're going to take those summations as we go up to infinity. So let's go ahead and calculate this, right? So we had a if I unhook the mouse, the IT people are going to come at me. All right, so this is what we had originally, right? You guys mostly agree with that? So that was our original signal. We didn't really put very good units on it, so let's go with time, and let's just go with x and x. Units in this are kind of tricky, and I want to add them, but I don't know how. So an autocorrelation function, right, is going to be the product between one point and then a point further along. And so if we think about this for a set amount of tau, right, so tau is our offset. So here's tau, and here's tau, and here's our RXX and our RXX, right? So our autocorrelation. So if you take a sinusoid, original signal, and you have a tau of 0, you have a point and you have another point right next to it. What is your correlation between those 2 points? Or your point and the actual point that it is? What's the correlation between you and yourself? 1, right? So it's going to start at 1, right? And then now you can start to see, okay, I'm real close between this point and this point, I'm real close, right? I'm like a 0.99, right? So I'm going to come down a little bit, but as I get farther away, I'm going to, I have pretty much no correlation between here and the peak, right? So that's an issue. So it's going to come down like this, right? And then once we get to a point where we start to have a correlation again, you're going to have a strong correlation here. So here in half your cycle, you have a strong correlation. But that's going to be, let me make sure I get these plots right. So did I not quite get that? So I have a correlation. Okay, so I've got a correlation that looks like this. Just draw the whole thing. Right? And they're a little bit out of scale, so it's a little hard to see. But I guess what's important here conceptually, so this is figure 11 in the notes, which is much cleaner. And you can compare that to figure 10 here. Right? But what you want to think about is this goes from 1 to -1 to 0. Right? And sometimes you're going to be very correlated, and sometimes you're going to be oppositely correlated. And it's as a function of tau. So it's how far we shift, right? So you can see that when I come back to a spot, so this perfect correlation here lines up here, right? So I'm moving in the right direction, and I'm at the same spot. This and this are perfectly correlated. Does that make sense? Right? But a little bit here, a little bit there, I'm moving minus and positive. Okay, so let's talk about the noise one. That's one we're interested in. So what's my correlation to my first point and my first point? 1. What's my correlation between my first point and my second point? Let's say my second point's here. Yeah, it really just kind of jumps all over the place, right? However, if it's pure randomness, noise, and we take that integral function, it should really be 0, right? There's no correlation because it's a purely random signal. Does that make sense? So this should look, and if you look at figure 11, it's a spike, and it's like kind of like crap like this because it's actually calculated. But a theoretical one would be kind of right down the middle at 0, right? And that's because, think about it, there's no correlation in a random signal. Your previous data point has absolutely nothing to do with your data point before. Yeah, go ahead. Question? So your negative correlation comes from the fact that, let's see if we can extract this out. Like, how do you have you're lined up, but you're moving in the wrong direction. Although now I'm looking at this limit equation and trying to see where I get that from.
So just depending on the direction.
Well, I mean, you can have a negative correlation when things are just moving the wrong way or around the flip side of the axes. I need an example to explain that. That would be a good example for the notes. Does that answer work for now?
Yeah.
Sorry. Yeah, that's a really good question. Let me put that in my notes. There goes my weekend. So. Yeah.
From the correlation function, like the 1/t that we have in front, wouldn't that drive the whole thing to 0 as we move to infinity? All the time?
No, because that's just we're in tau here. The difference between t and tau. The t is how long you're sampling over, and that's what we want to find. Yeah.
So if T does equal infinity, will the correlation eventually grow because it'll be like less random?
No. So if you have a truly random signal, there's no correlation. So the correlation is between one point and another point, right?
So it's not just regular.
Yeah, it's not over the entire signal. So this is the correlation between the first point and the rest of the points in that signal. Does that make sense? Yeah, and I think the best way to just come back to it is pure random noise has absolutely no correlation between one data point and the next data point, right? So there's no way to predict. It's like GameStop stock, right? Has no correlation to what was before or after. That makes sense? So at least conceptually, I hope that makes sense. And then this is this is in time, and this is in tau, right? So another way to look at this is you can kind of get that you have some correlation between this point and every point around this, right? You have some way to express that, and that's why you have some RxX function. But between here and every other point, you're not going to have any guess. That makes sense? Okay, so note that the value of tau, so you can see that the value of tau that you select greatly affects the correlation function. So it greatly affects the correlation of your sinusoidal input, right? So if I pick a tau, I may get a -1 or a +1 or anything in between. But the value of tau that I pick does not, that is not the case for the random input, where your signal is not correlated, and therefore there's little difference in changing the value of tau on the response of the autocorrelation function. That makes sense? And that's kind of what we should expect conceptually, right? So when we look at a sinusoid, there's going to be a periodicity to the signal. So let's take the Fourier transform of the autocorrelation function. Right, we're interested in the random signal. Right? So our next step here is to take the FFT, or sorry, the Fourier transform, not the FFT. So we'll take the Fourier transform, take the Fourier transform of RxX to get our power spectral density, PSD. Power spectral density. Did that a little backwards, but that's fine. And that is our spectrum, so S, of our variable, XX, is equal to 1 over 2 pi from -infinity to infinity of R XX tau, right? Because our tau changes. Our tau is what's driving the value for RxX. E to the -j omega tau d tau, right? Because now we're taking this with respect to our shift, right? So what is the correlation between one point and a point before it, or technically behind it also, but we don't kind of plot it that way. So if we look at a function of doing this, right? So let's go ahead and take our PSD for our two plots. So let's take the power spectral density of our two plots, right? And so for a sinusoidal loading, we have a correlation between one point and the point ahead of it that is a function of the frequency of our signal, right? That should make sense. Depending on how fast our signal is changing is where we get the most correlation. So we're going to get the highest correlation at that frequency. And so we end up with a plot that looks like this, T, a very high spike at the at the frequency of our signal. Let's just call that I don't know. Sometimes I just gotta do that. Okay. So let's just call that, you know, omega n, because we're kind of working with vibrations, right? But it's whatever the frequency of our signal is. Okay, so what are the units for PSD? It's a little confusing, but it depends on what your units coming into the system are, right? So we just look at our power spectrum density, and we don't consider it to be for energy. And let's say we're measuring our accelerometer in terms of voltage. We're going to have signal squared per hertz. So let's just go, let's say our signal is measured in voltage. It's going to be voltage squared per hertz. You'll see that most people leave it off. And the reason for that, it's really more of a relative measurement, right? It really matters where your peaks are and how big they are compared to other things. It's not a real qualitative measure. So, I mean, voltage squared per hertz doesn't really mean anything. Yeah?
That's right. Is the x-axis T or
T. No, frequency. Thank you. Yeah. Frequency hertz. All right. So now let's go ahead and look at the power spectrum density of our random signal. Right? So if we had a perfectly random signal, we had zero correlation, right? We should have no real signal here, right? But that's impossible because there's always going to be some kind of mathematical correlation. And so you're just going to get something that's very random, right? So maybe like this. Whoop. I like how I'm trying to calculate like my plot, but it doesn't matter. Something like that, right? But what's important is how low it is. So here, when we calculated this before, because this is almost a pure sinusoid, and the only numbers we're missing are just kind of rounding errors. When I did this in Python, I got like 0.97. That's my value here, right? This top value here, 0.0004. So this is this is in the noise down here. That makes sense. Okay, and that's a good power spectrum density, right, for a completely random noise, for a white noise. But it's a little hard to deal with in terms of mathematical, calculations, and we have a lot of points. So what we want to do is we can just take an average for it right down the middle. I don't like that. Maybe let's just do a fat line. Oh, that looks much better. Right down the middle and call that S0. And that's going to be the average of our signal. Right? So, and I know we talked about white noise before, right? But white noise has every frequency component in it. And so if our original input was purely white noise, then we should have a perfectly flat line here at S0. But you're not going to get that. But this is pretty good, actually. So if you hook up like a function generator, and put it to the white noise button, you won't see anything nearly this flat. It'll really have some peaks and downs. And it also depends on how long you sample, right? But that's pretty good for a white noise signal. So the flat frequency response in the frequency domain, right, is donated S0. So, this could be, it could be SFF of omega is equal to S0, or SXX of omega is equal to S0, right? So what's SFF? What would that be? What's function F? The force, right? So if you have a spectrum of your output X or the spectrum of your input F, right? Or whatever you want to call it. You can have spectrums of anything, right? You can have broadband internet is a spectrum. It has broadband. AT&T's internet company that they spun off is now Spectrum, Spectrum whatever. They pick a really basic engineering name and sell you internet under that, right? So, this is the same thing we talk about broadband internet, broadband excitation, broadband damping. We're talking about spectrums in that sense. And so the subscript is just denoting what variable the spectrum is for. So SXX is the spectrum of the response function. So for a 1 degree of freedom considered here, we can express the arbitrary input as a series of impulses, right, as discussed before. This knowledge along with the response that the function can relate the spectrum of the input, SFF, to the output, SXX, right, allows us to build this into equation. Again, the idea here is that we can just model this box, model this spectrum as a series of inputs. Does anyone disagree with that statement? Right? So we can do anything with a series of inputs. We showed that with the hammer example. And so we end up with this nice equation where SXX of omega, our spectrum of our output in the frequency domain, is equal to our transfer function for j omega, the absolute value of that squared. That happens because we're in the spectrum domain, kind of like how that voltage is squared. And we won't derive that. I should work on those notes, but it's really long. So there's no point to kill a whole week on that. Times 1 over 2 pi, negative infinity over infinity, R FF, that's the autocorrelation of our forcing function. That should make sense, as a function of tau. And then e to the negative j omega tau d tau. Right? Gonna need a box here, aren't we? So we can simplify this form into something that's a little bit more useful. Of particular interest here is the fact that we have an autocorrelation of our forcing function. So we know we can take, how do we get from the autocorrelation function to a spectrum? what step do we take? Yeah, the Fourier transform, right? Let's take the Fourier transform of the right-hand side, and then we end up with our spectrum xx of omega is equal to h j omega absolute value squared times our spectrum ff of omega. Okay, so this all of a sudden becomes incredibly useful. If I know my spectrum of my input and multiply it by my transfer function, absolute value squared, I get the spectrum of the output, right? Again, I have absolutely no idea on where the system will be at any given time, but I have knowledge of how this responds in the frequency domain, which is incredibly useful.